I was talking about these microwave vessels and the focused microwave technology. Now, in this what happens that the tough the material of the digestive vessel is, the better it is. So, that there is no leaching from the vessel, and that is why a borosilicate glass or quartz vessel or polyteflon vessel is most ideally suited for this kind of digestive vessels. Similarly, there can be a programmable method of adding different acids to this vessel, and these different acids should not react with the vessel material. So, that is why it is a very unique kind of machine which is in the latest trend to be used for metalloid extraction. But there are certain difficulties, because no method is foolproof. If there are advantages, there are certain disadvantages and difficulties with any analytical methodology that is developed. The main difficulties of focused microwave are the distribution of radiation between all cavities when they are simultaneously operated, and the elevated acid concentrations of the digestate. The former aspect is not so critical, because the control of the release of microwave radiation to each cavity is based on temperature of the reaction vessel. On the other hand, the acid concentration is high, because usually a large volume of concentrated sulfuric acid is required at atmospheric pressure operation in order to reach high temperatures. This aspect can be overcome by changing the usual procedure that recommend the programmed addition of concentrated acids to the sample. Concentrated acids can be heated by microwave energy, and the sample aliquot can be gradually added to this aggressive medium. So, now it is not necessary that all the acid should be added in one go and then microwave is passed through it. The microwave energy can heat it up very largely, and it would create lot of fumes of the acid. Instead, this can be programmed in such a manner that small volumes of acids will be added, and the efficient digestion will still take place without taking a bulk of the acid. Extraction procedures. Speciation analysis has become an important aspect in environmental and analytical chemistry. Speciation was defined by IUPAC as the analytical activities of identifying and or measuring the quantities of one or more individual chemical species in a sample. So, the word speciation, which I have been using all along, you should also understand the meaning of this. It means that we are trying to identify one or more individual chemical component in the sample. A successful leaching or extraction procedure prior to speciation analysis requires the preservation of all original compounds, such as organometallic compounds. These compounds can be extracted using focused microwave system that allow a careful control of the energy delivered to the reaction medium. It is therefore imperative to control both the power applied and the exposure time to avoid the degradation of any compound as well as the formation of artifacts. The integration of dissolution, extraction and derivatization in a focused microwave system may bring new dimension in sample preparation for speciation analysis. So, now you see that it is so well designed that it mildly reacts with organometallic species without disturbing the organic part of the molecule, which can be later on analyzed. It only specially takes out the metal and does the speciation of the metal. Inorganic and organometallic analytes. Focused microwaves are extensively used for sample preparation before the determination of inorganic and organometallic analytes. Extraction procedures can be carried out in environmental, industrial residues and clinical samples after a preliminary step of sample preparation based on the use of focused microwave system. So, you see that they can be used for environmental sample, for industrial residues and for clinical samples. So, there is a large variety where the focused microwave can be used, and it can be used for inorganic samples as well as organometallic samples. For example, this system can be used instead of conventional Soxhlet procedure, allowing a fast, simple and reliable sample preparation using low volumes of organic solvents and consequently generation of less hazardous residues that are expensive to discard. So, it has an advantage that it not only uses very small quantities of organic solvents for dissolution, and therefore, the disposal also is not very difficult. Organic analytes also can be treated. Microwave assisted heating in closed or open vessel reduce drastically solvent consumption and leaching times. In addition, recoveries of analytes increased when using focused microwave heating compared to other extraction techniques such as Soxhlet using conventional heating, sonification or supercritical fluid extraction. However, the formation of artifacts by thermal degradation should be investigated in spite of the suitable control of energy delivered by the magnetron. It is to be understood that whether it is organic analyte, inorganic analyte, organometallic analyte, every time there is a new sort of parameters that needs to be controlled. There is no hard and fast one method that will dissolve all the species, all different types of samples, and that is why I have taken up one by one, so that you can understand very carefully that if there are inorganic and organometallics, what is the condition that should be applied, and if the samples are organic in nature, what is the condition that needs to be applied, and what are the parameters that needs to be taken into consideration. As previously mentioned, focused microwave heating can be applied to carry out simultaneous extraction using multi-vessel system. Vessels can be built up using borosilicate glass, quartz or PTFE, that is polytetrafluoroethylene. It is a kind of a white plastic which is very sturdy. Microwave heating can also be applied as a cleanup procedure before chromatographic analysis. So, even there microwave heating helps to discard a lot of junk material before taking to chromatographic techniques. So, it can also be used as a cleanup methodology. Digestion procedures. Focused microwave ovens can be employed to assist the total digestion of organic and inorganic samples. Some advantages of this system have been highlighted before. The efficiency of the digestion can be improved by sequential addition of different reagents during the procedure. Now, I will give you an example. What happens is that when there are certain metal or metalloids which are very well embedded in the biotic material, they do not come out with just using one acid, and combination of acids and sequential addition of acids needs to be done in the reaction vessel, and focused microwave is being subjected to these vessels. What happens is that in every step more and more gets digested, and at the end of the such designed recipe, the maximum amount of speciation takes place. Organic samples such as oil generate large amount of gas during acid digestion. The use of focused microwave ovens makes possible to digest large sample mass without any safety problems. The digestion efficiency can be improved by the addition of sulfuric acid to reach temperatures as high as 250 degrees centigrade, and since it is a closed system and it has a vent which is thrown off out of the laboratory, it is much safe because those fumes are not entering the laboratory. The feasibility of working with a large sample mass was also exploited for the determination of radionuclides in soils, which are in this case required to be done at a trace level of the analytes. Different digestion methods can be optimized using focused microwave ovens. Now, radioactive compounds, when they have to be extracted from soil, even then this focused microwave works very efficiently and very well. This is how the schematic microwave radiation distribution inside a vessel looks like. You see, this is the frontal view, this is the side view, and from the sides the microwave energy is going on bombarding it or reacting with it. Sample addition to hot reagents. Another alternative to decrease the final acid concentration to digestate is to modify the conventional procedure and to add gradually the liquid sample to a small volume of concentrated acid. So far, we were taking the sample and adding the acid into it. Now, this is another method that already heated acid is taken in the Teflon vessel or the borosilicate vessel of the microwave digester, and to that the sample is gradually added. Small volumes of concentrated acids are taken, they are heated by microwave action. This strategy can be easily implemented using standard equipment and has some interesting implication. Now, what happens when we do this reverse addition? Digestion of greater volume of sample using a smaller volume of acid is possible, because already the acid is heated up, and so it has a better digestive power as compared to a cold acid which is gradually added to the hot sample. Each sample aliquot is partially digested before adding the next one. Digestion is carried out in a more concentrated acid media because the reagent is less diluted by the solvent. The acid is in excess compared to the sample during all digestion steps. Hot concentrated acids can generate reactive radicals that can speed up the digestion process. Lower blank values and better sensitivity due to lower dilution of digestates is possible. So, you see there is also an advantage in this reverse addition. So, we can conclude that focused microwave ovens are not as disseminated as cavity microwave ovens. However, there are some applications that could be performed better on the former system, that is focused microwave is sometimes better than the cavity microwave ovens. Sample preparation for speciation analysis can be improved using a focused microwave oven owing to a better control of the energy delivered to the sample. Extraction procedures using diluted acid or organic solvents at low temperature can easily be carried out in focused microwave ovens. Additionally, total digestion of either large amounts of samples or samples rich in organic compounds can also be performed in open vessel operated at atmospheric pressure. The conventional procedure can be modified by gradually adding sample aliquots to hot concentrated acids also. So, there is lot of permutation combination that can be carried out doing this using the focused microwave ovens. This strategy decreases the amount of acid and simultaneously increases the sample volume that can be digested. So, you see there is a distinct advantage that this helps to use lesser amount of acid. At the same time, the sample volume can be large, sample volume can be digested. Finally, focused microwave oven can also be applied for acid vapor digestion in a single vessel procedure also. It can be concluded that the use of focused microwave ovens probably will be extended, and it can become a standard tool for sample preparation in speciation analysis. So, if we have to target speciation analysis, focused microwave ovens are the answer for the analyst and the choice of method for the analyst. We have been talking about supercritical fluid extraction, a critical review of its analytical usefulness. I am going to talk about this because in the last few lectures I have been talking about one very major effect, that for extraction supercritical fluid is one of the best methods. But let us try to look why it is better than others. How is it better? Because just by merely understanding or knowing the name, it is not enough. This is one of the most recent trends of extraction, and as the name suggests, supercritical fluid extraction, it is very useful analytical tool for analyzing not only inorganic sample or organometallic samples, but also organic and inorganic samples. Supercritical fluid extraction, SFE, it will be referred as that all along. The evolution of supercritical fluid extraction is very recent, since 1990. In order to pinpoint the reason for its rare implementation by routine analytical laboratories, despite its high analytical potential, we identified various reasons and we propose ways to overcome the shortcomings behind them. We also discuss the great analytical potential of the SFE and justify its use for routine work. I will give you an example. We were facing a lot of problem in the extraction of a natural dye from eucalyptus bark, and whenever we were boiling the eucalyptus bark, we were only getting dark brown extract. Then we thought, why not to put it and do a solvent extraction, but again in the solvent extraction, that is the Soxhlet extraction, we were getting only dark brown extract. So, the aqueous extract was also giving dark brown and the solvent extract was also giving dark brown. But when the solvent extract was column chromatographed, there was a band which was coming as yellow color. So, we thought that along with the tannins, which is brown in color, there must be a yellow compound. Now, how to specially analyze or extract this yellow? We were just pondering over this extraction challenge when we came across this supercritical fluid extraction. We did not have this extractor in our laboratory. So, I sent the sample to IIT Bombay, and there we were able to extract and get beautiful yellow dye specially only with that. So, that means that it is one of the methods of uniquely separating the one specific compound when there are arrays of compound, and rightly so. The woman who works at IIT Bombay, the scientist, also has written up a book, and she has shown that from one particular plant material, which may be having essential oils as well as dyes as well as other terpenoids, it can specifically extract one by one at different parameters from the same plant material. So, by stepwise extraction at different parameters, one can get different compounds, and thus from one plant material very useful value addition products can be obtained. Supercritical fluid extraction. supercritical fluids can be used to extract analytes from samples. The main advantages of using supercritical fluids for extraction is that they are inexpensive, contaminant free and less costly to dispose safely than organic solvents. For these reasons, supercritical fluid carbon dioxide is the reagent used to extract caffeine from coffee. Now, you will think that carbon dioxide is a gas. How is it that I am saying that it is a supercritical fluid? Yes, when carbon dioxide is compressed, the gaseous body is then compressed into liquid, and further if it is compressed, it becomes solid. The properties of supercritical fluid also provide some advantages for analytical extraction. Supercritical fluids can have solvating powers similar to organic solvents, but with higher diffusibility, lower viscosity and lower surface tension. The solvating power can be adjusted by changing the pressure or temperature or adding modifiers to the supercritical fluid. A common modifier is methanol. Typically 1 to 10% methanol can be added to this liquefied carbon dioxide, which increases the polarity of the supercritical carbon dioxide. So, whenever, as what I mentioned, the different types of compounds are actually differentiated on the terms of their polarity. So, at a particular condition only supercritical carbon dioxide can extract. At another condition, the 1% of methanol addition to the supercritical carbon dioxide can extract. Another situation can be that 5% of methanol when added to supercritical carbon dioxide can extract the third type of compound. Physicochemical properties of the supercritical fluids. Now, what makes them different from normal fluids? A pure supercritical fluid is any compound at a temperature and pressure above its critical value or critical point. Above the critical temperature of a compound, the pure gaseous component cannot be liquefied regardless of the pressure applied. The critical pressure is the vapor pressure of the gas at the critical temperature. In the supercritical environment, only one phase exists, the fluid phase, as it is termed. It is neither a gas nor a liquid, but it is a fluid and is best described as an intermediate of the two extremes. That means, it is not a gas, it is not a liquid, but it is an intermediate or an in between stage of the two, and this happens only at a particular temperature and pressure for a particular compound. This phase retains solvent power approximately as like liquids, as well as transports properties like the common gases. A comparison of typical values for density, viscosity and diffusivity of gaseous liquids and supercriticals is presented. So, you see that the density also increases, the viscosity also increases and the diffusibility also decreases. It is more diffuse, so it decreases, and it is thus between the gaseous and the liquid, as what is shown in this slide. Now, what happens that this is a very typical supercritical graph where liquid and gaseous are shown. So, this is the stage at which the supercritical fluid exists. Why supercritical fluid extraction? What is so special about it? The supercritical fluid extraction has been applied only recently to sample preparation on an analytical scale. So, as I told you, it is very recent, only in 1990s it was, or 1980s it was discovered, and it took some time for people to adapt and to understand its usability. This technique resembles Soxhlet extraction, except that the solvent used is a supercritical fluid, substance above its critical temperature and pressure. This fluid provides a broad range of useful properties. One main advantage of using supercritical fluid extraction is the elimination of organic solvents totally. thus reducing the problem of their storage and disposal. Furthermore, several legislative protocols such as EPA Pollution Prevention Act in USA have focused on advocating a reduction in use of organic solvents which could be harmful for the environment. So, you see why it has an edge over sock slit. Sock slit extraction totally uses only solvent and large volumes of solvent. So, if there is a technique which is using recycling of its own gas by rarefication and contraction of the same gas, the solvating power is increased and decreased, and so when it is the fluid, when it reacts with the plant part, extracts certain compounds and it is transported, and when the gas is rarefying, then it is rejected out or dissolved. So, this is a beautiful example where solvent has been drastically used only as a modifier, only 1 to 10% methanol or ethyl acetate are used, which are known as entrainers or modifiers with supercritical fluid of carbon dioxide. Efficiency in sample preparation. Because supercritical fluid extraction has several distinct physical properties, it is regarded as promising alternative technique to conventional solvent extraction. Some of the major advantages summarized are as follows. Supercritical manifest higher diffusion coefficiency and lower viscosities than a liquid sample. As a consequence, solubilities and diffusivity in such fluids tends to be much higher than in liquids, resulting in comparatively fast reaction kinetics. In SFE, the solvating power of the fluid can be manipulated by changing the pressure and temperature. Therefore, it may achieve a remarkable high selectivity. This tunable solvation power of supercritical fluid is particularly very useful for the extraction of complex samples. I just gave you an example that how from one plant material the essential oils and the dyes can be separately extracted without contamination, and there is no need for any further chromatographic purification. Why? By simply manipulating the temperature and the pressure, the solvating power of that supercritical fluid at that point of time is just ideal to extract one type of compound, one nature of compound. And then when the parameter is changed again, it is more suited for the second type of compound. In SFE, a fresh fluid is continuously forced to flow through the sample. Therefore, it can provide quantitative or complete extraction. Now, as I told you that when it is in the fluid state, carbon dioxide, it has a great solvating power. So, it picks up one type of compound, but when the gas is allowed or the fluid is allowed to rarefy, then it kind of drops the compound which it has solvated or taken along with it, and that is why it can be recycled, and every time a fresh fluid is entering the plant to be extracted. Coupling SFE to integrate sample preparation and analytical determination. So, how can we use this particular technique for the sample preparation and for analytical determination? One of the greatest advantage of SFE over other sample preparation technique is that it can be automated. This makes it highly suitable for fast and routine analysis. The efficiency of the different SFE collection models in online assemblies is very important, as it provides quantitative transfer of extracted analytes to the analytical instrument and reduces contamination levels. 4 different ways of collecting SF extracted analytes have been proposed. Solvent collection in a vessel for adjusted flow control coupled with water liquid trap for the extraction of glycosides from grapes, Second method is solid phase collection, which is accomplished by depressurizing the supercritical fluid at the inlet of the column packed with an inert material, that is stainless steel beads or fused silica capillary, or an adsorbing material such as octadecyl silica ODS, or diols or silica gel or fluorosil, tenax or alumina. After the extraction has completed, the analytes are eluted from the solid phase trap with a suitable solvent. One advantage of solid trapping is increased selectivity that can be further improved by coupling a selective trap with a selective eluent. For example, polar compounds can be trapped on silica gel column and subsequently eluted with appropriate solvent. Now, either it can be collected in a collector or it can be actually taken over on a solid phase and adsorbed on it, and further with the little amount of solvent it can be dissolved or eluted from that. So, there are many ways of adapting the supercritical fluid extraction methodology so that it can serve the purpose. Other methods: solid liquid phase collection, which uses a solid phase trap followed by a vessel containing a solvent. This is well suited to highly volatile analytes. The losses of analytes from the solid phase trap are collected in the vessel holding the solvent. Husser et al. Demonstrated that solid liquid trap can minimize the losses of polycyclic aromatic hydrocarbon observed with some liquid collection devices. So, what he did, he found that there were some losses because of this transfer business. So, he tried to use another kind of trapping or collection system where solid liquid collectors were used. Otherwise, empty vessels trap can also be used. With one or more or several empty vessels and dispensers can be used, and which need no removal of the solvent. Simply the extracted component is collected, but it is time consuming, because every cycle it will come and then it will just dissolve, and this goes on for several cycles. So, it may take a little longer. If there are solvent traps, then it is much faster. Advantages: the SF extractor to an analytical detector provides several advantages that can be named. Large amount of extract can be passed through the instrument, virtually 100% can be transferred in a direct manner. Little sample manipulation is required, thus avoiding analyte losses. Increased throughput, that means the output of the reaction or the extraction is very high. Those samples requiring it can be protected from light and air. Some are very light and air sensitive. Now, because this is a pressurized system, it is a closed system. So, air contamination or air oxidation or moisture oxidation or light effect can be avoided. Substantially reduced amount of solvents are used. As I mentioned that only under very special conditions where simple supercritical carbon dioxide is not very effective in extraction, 1 to 10% of methanol or ethyl acetate type of solvents are added as entrainer or modifier. So, you see very small quantities of solvents are required. The coupling allows the development of sample screening methods, thereby avoiding the need to chromatograph every single extract in routine analysis. So, as I mentioned that these are the methods where sometimes it is so pure that no further chromatographic technique is required. Therefore, supercritical fluid extraction, as you would also appreciate, has a certain demarcated advantages over the Soxhlet and the conventional extraction methods. SFE and sample screening methods. The availability of fast, reliable screening method is an important prerequisite for screening or increasing the number of samples to be analyzed when there is an urgent need for the results. SFE has been recognized as an effective alternative to liquid-liquid extraction for the isolation of analytes from a variety of matrices. The combined liquid-liquid solvating capacities and gas-like transport properties of the supercritical fluids can provide efficient, fast extraction of analytes, thus simplifying the analytical process to a great extent. Now, I will give you an example. Fat in skimmed milk, whole milk, cocoa and leather was monitored in a screening system. Samples being fully treated with supercritical fluid extractor. Fat in the milk sample was trapped in C18 cartridge and automatically rinsed with hexane. Fat in leather was trapped in stainless steel balls and eluted with a mixture of hexane and methylene chloride. The analytes were injected into a solvent stream in a simple flow injector module to measure a response in a piezoelectric detector. The limits of detection thus achieved were 0.001% and 0.0007%. So, you see it is so efficient even in simple sample screening methodology. Thus, we can say that if we look at the investment, process time, solvent consumption, method development, sample treatment, and we make a comparison between a Soxhlet, a microwave assisted accelerated solvent extraction and supercritical extraction, you will see that in all respect supercritical fluid extraction has an edge over all these three different types of practiced methods. World over, in industry and in many other food and industrial and miscellaneous and environmental samples from the year 1993 to 2002, the advantage of using and the propagation and the popularity of supercritical extraction has increased enormously. Application of supercritical fluid extraction. Supercritical fluid extraction is not widely used yet still because the machine is very expensive. Although it is a one-time expense, but still it is not taken up as much as what it should have. But as new technologies are coming up, there are more and more viewpoints and could justify it, as high purity, residual solvent content, environmental protection are the basic ideas behind using supercritical fluid extraction. The basic principle of supercritical fluid extraction is that when the feed material is contacted with the supercritical fluid, then the volatile substances will partition into the supercritical phase. After the dissolution of the soluble material, the supercritical fluid containing the dissolved substances is removed from the feed material. The extracted component is then completely separated from the supercritical fluid and by means of temperature and pressure change. That means, it is rarefied. The supercritical fluid then it may be recompressed and reused. So, it can be recycled for the next extraction process. So, it is also economical. Only very small amount of carbon dioxide is lost in the entire cycle. So, after several cycles the gas can be replenished. Merits and demerits. So, as usual there are advantages. Advantages. Dissolving power of supercritical is controlled by pressure or temperature. Supercritical fluid is easily recoverable from the extract due to its volatility. It is non-toxic solvent and leaves no harmful residues. High boiling components are extracted at relatively low temperatures. Separations not possible by more traditional processes can sometimes be affected. Thermally, liable compounds can be extracted with minimal damage, and there are of course some disadvantages. Elevated temperatures, elevated pressures are required. Compression of the solvent requires elaborate recycling measures to reduce energy costs and high capital investment for the equipment, as what I mentioned.